Hey everyone, so today we are going through the 2023 paper for probability distributions, and we are going to be going through all the questions, answering them all in detail, so you guys can pick the ones that you guys are struggling with. What I recommend for the best learning experience is that you guys pause the video, do the question yourself, and then you guys can skip forward and see if the answer is correct, and if not, watch my way of doing the question and take some notes afterwards. So I'll see you in the first question. Okay, so question 1, let's have a look. There are many sheep farms in New Zealand where animals graze on pasture all year round. The stocking rate is defined as the number of animals grazing on a given amount of land. For sheep being farmed on New Zealand hills and mountains, average stocking rates are about 9 sheep per hectare. Use a suitable probability distribution to estimate the probability that there are more than 10 sheep on a given hectare in New Zealand hills or mountains. State the name of and the parameters of the probability distribution as part of your answer. Okay, so when you guys go through them, just have a look through all the different options of your probability distributions. So for example, here we know sheep, we can count sheep. So the number of sheep is not continuous. We can't have 0.5 sheep. So we already know that it has to be binomial or it has to be Poisson. And if we have a look at the question here, we need to fulfill the parameters of each of those distributions. So, for example, the binomial distribution needs a number and a probability, which we don't have. And what does the Poisson distribution need? The Poisson distribution gives an average. Lambda is the average, which is the mean. So that's exactly what we have here. So let's write that down. Let's say x here is our random variable. Maybe I'll do it in blue. Sorry about that. And of course, I can't get rid of that one. There we go. So x has distribution Poisson. And in brackets, we're going to write down our parameter. There's only one parameter. By the way, if you forget what the parameters are, go to the formula sheet. They are listed there for you. So here we have 9 is the parameter, and that way we've already named our distribution, and now we just need to answer the question. So let's have a look what we've got. Here we want to find the probability that there are more than 10 sheep on a given hectare. So we're just going to find the probability that our number of sheep that we have with x is greater than 10. And all you guys need to do is put this in the calculator, but you guys need to remember that the calculator can only do this sign or the equal sign. So these are the only ones that the calculator can do. So we have to think about how this works. Well, everything greater than 10, that means 10 is not included. So that means 11, 12, 13, and so on. So what would be the opposite to this? Well, this would be everything below. So this one here is our probability statement here. The opposite is everything lower. And we do want to have a probability statement where we have less than equal to a number. And here that number would then be 10 because everything else here would not be included anymore. That would be the opposite. So we're going to get everything below 10, including 10. So now we have this situation here. And now we're going to have to remember that if we solve for the opposite, then the probability is actually 1 minus the opposite. So there we go. Let's put this in the calculator and solve for the correct answer. Where's my calculator? There we go. We're going to go to Stats menu, Distribution, which is F5. And we're going to go to the Poisson distribution, which is F6, then F1. And if you guys remember, we have PD and CD. So I'll just write this on the screen here. You have PD and CD. PD is the probability distribution function. CD is the cumulative distribution function. So for these ones here, this first one is the equal situation where we have a probability that x has the value little x, and the cumulative distribution is when we have the probability x is less than equal to x. So let's take this with our question. We have less than equal to, so we need to press CD and make sure your first part here is on the variable and not list. If you want to change it, it's F2. And now we enter the x. So that's the value 10 here. And the mean is number 9. So let's put that in. Okay, enter, and now we get our probability. So we have 1 minus 0.70599, I guess. So we are going to do 0.2, 1 second, 29401. There we go. Okay, so now this is now our probability for having 10 or more sheep in a hectare. By figuring out the distribution here as well as the correct answer will give you guys an achieved mark. You need both of these. If you need extra support with your studying, join our free Discord community where you can ask questions, get help, and even request me directly for one-on-one tutoring. Inside the Discord, you'll also find a full resource hub with worksheets, study guides across different subjects, and I highly recommend checking out my website where I've put together full courses organized in order so you won't miss any of the topics. You'll find both links to the Discord and the full courses right below in the description. Alright, this is the second part of the question. It has been commonly known that sheep tend to flock together and form groups. Give 2 reasons why this piece of information may affect the choice of the probability distribution and its required conditions for modeling the number of sheep per hectare on New Zealand hills and mountains. So remember, when they talk about assumptions or reasons for a distribution model, you need to go back to commenting on what is required for those distributions. So for example, for the Poisson distribution, we need independence between each of these. Yeah, so we need independence. And I'm not going to write them down in detail. We're just going to talk about it so you can kind of see what you have to put in. So the sheep, each sheep here on the field is maybe dependent because they flock together. That means that in one area we're going to have more sheep than on another area. And that is not what the Poisson distribution requires. We require that each of these people or each of these objects, in our case sheep, is random and independent from each other. Yeah, so random is our second reason here. Yeah, every sheep needs to be randomly allocated on our field, ... There we go. But random is not the case because we know that they form groups. That means we more likely have something that's happening like this, where we have some groups, maybe another group over here. Yeah, so the Poisson distribution requires that we are having randomness. There's a couple of other things you guys may be able to say. Here you can comment on the parameter. Yeah, so lambda in our case was equal to 9. May be different, right? May be different. Sorry, I'm going to try and write this a little bit better. Yeah, it may be different across different fields or so on, different hectares. Yeah, so we might not be able to use the same lambda for all of New Zealand hills and mountains. Okay, cool. Next question. Can that fit? Yes, perfect. So, Awasi sheep are a rare New Zealand sheep breed with origins in the Middle East. They are predominantly milking sheep, although they also produce wool that is suited to the carpet industry. Wool finesse is the measure of the diameter of the sheep's wool fibers in microns. Figure 1 shows the frequency distribution of wool finesse for a sample of 49 of those Awasi sheep. So you guys can have a look at the graph. We've got the frequency on the left and the wool finesse at the bottom. Okay. Suppose a uniform distribution is chosen to model the wool finesse of Awasi sheep. Use the probability distribution to calculate the probability that for a randomly selected Awasi sheep, the wool finesse is greater than 35. Cool, awesome. Okay, so the first thing we need to write down is the distribution. So we have uniform. And then in brackets, we're going to have to put the parameters. Here it's the minimum and the maximum. So let's have a look. They told us, if we look at this, we have a minimum of 20. Yeah. So we're going to have this value here is our minimum. Here we have a maximum. Yeah. So what are we going to do? A is the minimum, is 20. We can write that down. B is the maximum, which is 60. And we've got our probability distribution done. Now, what we need to do next is calculate. Remember that this kind of looks, I wouldn't draw it really on here, yeah, but just to see, it's kind of a uniform, it's a rectangle. So if we have a rectangle, that means we can calculate the area of our rectangle to find the answer. Yeah, so here at some point we have 20, then we have 60, and I'm just going to draw a rectangle for our distribution. Yeah, so here we have our x values, and here we have the probabilities. So let's have a look. If we wanted to know the probability that it's over 35, yeah, at some point we have 35 here. So let's go and have a look. Everything over 35 is this part here. So we're going to have to find the probability now that our x, our measurement for the wolfiness, is greater or equal to 35. Now remember, the equal sign is not required because equal sign included or not included for a continuous distribution is not necessary. Yeah, for a continuous distribution, normal, for uniform, for triangular, all of those, if you have the probability that x is equal to some number, is 0. So the equal sign doesn't matter. You guys can add it as you want. And because we have the rule that we want less than equal to or equal to for the calculator, we can do that. But now for this one, remember, it doesn't matter because we're not going to use the calculator to calculate the probabilities here. So how do we do this? We want the area here. So we have the area is base multiplied by the height of the rectangle. So from 35 to 60, how far is this? This one is 60 minus 35, which is 25. Hopefully I'm correct. Yeah, 25. And now we need to figure out what is the height. Yeah, so the height here is this part here. How do we find the height? Well, the height is given in the formula sheet, which is this part here. Yeah, this is our height over here. Now, if we look at this, let's make it in purple. I think that would be nice. There we go. Yeah, so this one here is our height. And our height is given as 1 over b minus a. So 60 minus 20, which is 1 over 40. So we can write that as 1 over 40. And if we put it in the calculator, then sorry, you guys don't see it anymore. There we go. Let's move it over. Let's go to our normal menu. There we go. It's going to be 25 divided by 40. And we can give a decimal, which is 0.625. Awesome. Okay, so for this question, giving the correct uniform distribution as well as the correct answer will give you guys, an achieved mark. Yeah, you need both of those for an achieved mark. Awesome. Okay, next question. So the sample data shown in figure 1 is run through a simulation model 1000 times, assuming that the wool model for a Wasi sheep is uniformly distributed. So we're going to assume a uniform distribution. The minimum is 20, the maximum is 30. I guess that makes sense. Figure 1b shows the results of the simulation model, overfitted shape of the model generated by the data, and original real observed data. The blue dots show the relative frequencies of the different classes of the wolfiness. The gray band shows the variation expected for classes in the wolfiness based on the total of 49 sheep and a quarter probability for each wool. So let's have a look. We need to comment here on, okay, so based on the results on the simulation model and the original real observed data, discuss whether the uniform distribution model presented above appears to be appropriate for the model, for modeling the finesse and for the Wasi sheep. So we need to have statistical reasoning as well. Yeah, so we need to explain and give reason for our thoughts. So when we look at this, this is kind of the same graph, right, as here, just with the blue dots. So the question is, does our distribution, which kind of looks like, I don't want to do it in blue, our distribution kind of looks like this, right? And the question here was, is this rectangular part, the uniform distribution, suitable for our data? Because clearly we have some of these values being above and below. So what we do is we sample this 1,000 times. We run a simulation to see what we would have if we had the uniform distribution. And remember, each of these sheep, the 49 sheep, is independent of each other. We're going to generate a number for this every single time. And then we have a number here, 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 and here, right, for each of these. So we can kind of see what we would get if we did this on multiple occasions. Okay, so the question here is, and if you guys seen the other videos in this kind of exam part, what we're looking for is kind of like the width here, right? So we want to have a look how wide this is, because this is possible values under the distribution. Yeah, even values this low are possible. Yeah, so and now we want to compare this to what we actually have, which is the blue. So I would say that every single one of these is within the possible ranges of our distribution, which we would say is possible that under chance alone, these are picked in that order. Yeah. So let's have a look at what you guys need to say here. You guys need to have one reason for an achieved and 2 reasons for a merit or excellence answer here. Yeah. Okay, so the first part that we want to have a look at here is we need to talk about the randomness being for each of these, yeah, for every single one of them. So let me write this over here. 1, 2. Let's see if we can make 3 points. We might do 2. Yeah. So first of all, we are happy, yeah? Happy with the model. The reason for that is because we are within the ranges, yeah? So this would be your explanation. That's what we kind of talk about here now, yeah? So we're happy with the model, and that's what you would say, because we are within the possible values under the simulation, within the bands of where the gray area is. Then you can also comment that it's not appropriate, but then you can only get an achieved because it is actually an appropriate model. Yeah, and what you could say is that here it's very high and here it's very low, and it's unlikely because there's so little amount of gray bands here. Yeah, but it's still possible. So we're going to say it is a possibility. It is a good model for the situation. We also need to think about this having a quarter probability for each wool class. Yeah, so they're all equally likely. Yeah, so everything is equally likely. So we have a fair, constant probability here. That's what our distribution wants. Okay. These are kind of the 2 things. So 2 is probably what we need here. Yeah. So we need to talk about the equally likely outcomes. Yeah. Which is our uniform distribution. Yeah. That it all is the same. Yeah. That is a tick. And we need to compare the values that we've had before and say we're happy or we're not happy with it. Having 1 comment here will give you guys an achieved mark. If you guys want a merit mark, you guys have to have a correct comment that it is appropriate and explain it. And in order to get an E, you guys have to explain this in detail and linking this back to the equally likely part for each wool class. Yeah, so that's one part. And potentially you can also say that the number here, 49, is large enough to make these simulations. Okay, now next question. Using an appropriate probability distribution model, calculate an estimate for the probability that the wool finesse is between 25 and 40 for each of the 4 Awasi sheep. Okay, so here we have 4 Awasi sheep, and they want us to pick a distribution to make it between 25 and 40. So if you guys commented before that you guys can use the uniform distribution, then you can just do that. X has distribution uniform, And then you have to put the parameters in brackets. Yeah. So what are the parameters? It is the beginning and the end, the min and max. Yeah. A is the min, which was 20, and B was the max, which was 60. Were that the correct numbers? Yeah, that's the correct numbers. Yeah. So now we've named and stated our probability distribution, and now we want to answer the question. So the probability statement here wants that the wolfeness is between 25 and 40. So we have x is between 25 and 40. And what we're going to do is we're just going to quickly draw our distribution again. We start at 20, we end at 60. This is a rectangle, and we want to be somewhere between those values, right? So how are we going to get that? Here's 25, here's 40. So we have this area here to find. Area is base times height for a rectangle. The base here is the number at the bottom. Yeah. So how far are these apart from each other? 40 minus 25 would be 15. And the height again is the formula that is in the formula sheet, which is 1 divided by b minus a. So we can put that together. 1 divided by b is 60 minus a is 20. And if we put that all together, we get 15 times 1 over 40. Remember, we already calculated that, but it's good to practice. So our probability is 15 over 40. And if you guys want to, you guys can put this in the calculator, and then you guys should get 0.375. Yeah. You can cancel things out here to make it 3 over 8. Okay. Now, we have the probability for what? Well, this is the probability of being between 25 and 40. But remember that each time you make these calculations, that is for one sheep, one object, one person, or whatever the question is referring to. But the question is actually asking us for 4 sheep. Yeah? It's asking for 4 sheep to be this. Well, we kind of assume that each of the sheep is independent. Yeah, so that means we can multiply the probabilities. So the probability of 4 sheep here that we want between 25 and 40 is then the probability 0.375 to the power of 4, multiplied by itself 4 times, because each sheep has 0.375 probability of being between 25 and 40 themselves. So let's put that into the calculator. Can't do this one in my head, so let's quickly change that over. There we go. So 0.375 power of 4. So we get 0.01978. Okay. So this is now our probability of having multiple sheep, 4 exactly. Yeah. So if you guys calculate the probability for 1 sheep, that is an achieved mark, and calculating it for 4 sheep will give you guys a merit mark over here. Very good. Awesome. Next question. Oh, and we're almost done with question 1. Very good. One of the assumptions needed for the calculations in part 3 is independence of events. Wonderful. Yeah, that's what we established as well. Identify the appropriate event and justify the assumption is in context. So here, what is the event that we're looking at here? So let's have a look. In the question before, we were looking at being between 25 and 40. Yeah, that's what we have for each of these 4 sheep. Yeah, so the event is that they are between 25. Sorry, I'm trying to make this a little bit better for you guys there. That we're between 25 and 40. And the question is now, is this independent for the different sheep? And whenever they talk about independence, you kind of just have to think about the context and trying to like make up things where things could go wrong. So could sheep somehow affect each other to see what kind of value we have for the finesse here? And none of us know anything. We're not farmers. We don't know anything about sheep. So you kind of just have to make some of these up, but they have to make sense. And as long as it's reasonable, whatever you're coming up with, they will give you the mark. So I would argue here that there's an issue. Yeah, so we have an issue with independence. Why? Because I would think that if one of those sheep is from one farmer, they might be breeding sheep, so they might in some way be in some way related. Yeah, they might have multiple females or one or multiple males that they use to breed the sheep with. So perhaps that will then cause dependence because they all have very similar genes. What we can also say is they live on the same area, right? They live on the same area, which means they have the same food, the same resources, the same environment, the same predators in the area, the same sicknesses, which would cause them to either all grow really well or all grow really badly together. And while that doesn't have to be for every single one of them, they probably are affected by the same situations here. Yeah. I'm just having a look. What else do they suggest? They suggest nothing else. Okay, so if you guys get an answer here and you get a correct identification for the event, then you guys get an achieved mark. And discussing why this may or may not be independent will give you guys a merit. If you guys find a valid explanation for this to be independent, then you guys can happily put that down. Yeah. A lot of the times it's easier to find an example for no independence because you can, just like me, make up some of these situations that could affect each other. And as soon as if you've got something that in your head or in your mind makes sense that they affect each other, then you're golden. Then you just write that. All right, we are back. Sorry, remember I can't record all of these in one go. I always have to do some other things. So let's get into question 2. The rate at which a hen lays eggs can be modeled by a Poisson distribution. Wonderful. Immediately mark this down. And 99.73% of the time, she lays at least one egg. Wonderful. At least one egg. Calculate an estimate for the average number of eggs the hen lays each week. Cool. So we have been given that the number of eggs here, X is the number of eggs laid, and that X has a distribution Poisson with parameter lambda. But we don't know what lambda here is. We don't know what the average number is. That is actually what we're trying to find here. Find an estimate for the average number. So we're trying to find out what lambda is. Now, there's usually in past papers only 2 situations where they ask you for the binomial as well as the Poisson distribution to find these parameters. The normal distribution is a little bit more difficult to find. Sorry, no, the normal distribution they have done in year 12 a lot, but they could ask you to find the mean and the standard deviation. Yes, but they do like for year 13, they do like to find the Poisson distribution or binomial. So in order to do this, we need to have a look at the formula sheet. And what you do is you go to the Poisson distribution and you have a look at the formula. And it says there that the probability that x is some value little x is given by a formula which is lambda to the power of x e to the negative lambda divided by x factorial. So it looks a little bit, it looks hard, but it's not actually that bad. Yeah. So just a reminder for everyone who's now looking, oh, I can't do this. You got this. Yeah. What is factorial? Just a quick reminder. Yeah. 3 factorial, for example, is the number 3, then the number 2, then the number 1, and they're all multiplied together. So 4 factorial is here 4 times 3 times 2 times 1 and so on, which is 24. So don't worry about the exclamation mark. Yeah. And usually they only ask you to do this for a certain number to make the calculation easier. This is not an algebra exam. But let's have a look what the calculation gives us. Yeah, we've been given here in the yellow that the probability of x being at least 1 is 0.9973. So at least 1 is this number. Now, if you guys remember the Poisson distribution, is infinite. So 1, 2, 3, 4, 5 into infinity is what this number is. Yeah. So we can't list them all and add all the probabilities up. What we want to do is switch this around. Yeah. So always think of the possibility of using opposites in these kind of questions. So if you guys need to check, yeah, in the formula sheet, does it say that? I guess it does not really say that it starts with 0. Yeah, x values are 0, 1, 2, 3. But if you guys look at the table, it does actually for the x values start with 0. So maybe as a reminder, if you can't remember, it is in the table on the left-hand side where the x values are displayed, where it shows you that you start with 0. So the opposite of 1 and more is none at all. So if we have none, and how do we do opposites? It's 1 minus, because they are mutually exclusive events. They complement each other to make 1. So how do we calculate this? Oh, sorry, I should probably, in order to calculate this one, that is 1 minus the probability of x is greater than or equal to 1, which is 1 minus 0.9973, which is 0.0027. Cool. Okay. Now, the last part here is that we need to use the equation at the top here and substitute in our values for x, which is these ones over here. I can't really go further. So the probability that x is equal to 0 is equal to lambda to the power of x is 0, times e to the negative lambda divided by x factorial, which is 0 factorial. And now you guys just need to remember that any number to the power of 0 is 1. So we have 1 times e to the negative lambda. And 0 factorial, 0 factorial is also 1. So we can simplify this already by just having e to the negative lambda. Multiplying by 1 and dividing by 1 doesn't change anything. And we've been given that that probability is 0.027. And now you guys can put this into the solver if you really want to. If you don't know how to solve this algebraically, yeah, you guys can just put this into the solver. And here, lambda is the one that we want to find. So that is going to be our unknown variable. So let's have a look on how to do that. We're going to go to menu, and we're going to go to equation because we're solving an equation. And we're going to go to F3 solver. And now at the top, I like to press delete first and delete everything, yeah? But then we can put our equation in. So 0.0027. And now the equal sign is at the very bottom somewhere on your calculator, which is here. So we're going to have shift the bottom button. And then E is the exponential button. And there's like a little yellow one. It's hard to see, but you guys can find it on your calculator. Shift natural log is the e to the x. And then in the top, we have negative. But then lambda is here x. It has to be x in the equation. So this button here, I think, usually works for x. Yeah, it has an x in it. The same as the button that has a red x. So this one here, if you do alpha plus, it also should work. Now we're going to press enter. And I usually press enter a couple of times until this actually works. I don't know why it is, but just remember, just press it a few times. 3, 4 times, doesn't matter. If you press it too much now, it doesn't matter. Once you're at the screen, it will tell you what x is. And in this case, of course, x was our lambda. So lambda is equal to 5.9. 5.9. Let's do 5.9145. Yeah, just to have some decimal places here. Now, if you guys are calculating correctly that the probability of 0 is this number, that will give you guys an achieved mark. And if you guys are setting the equation together, actually you guys need to figure out, you can't just calculate the number. It says you guys need to be on this step here to get achieved. You have to set it equal to the formula in the formula sheet and then substitute in the value 0. And then to actually get the answer, which you can do with a calculator, excuse me, there we go. Yeah, that will give you guys a merit. Okay, wonderful. What is the most likely number of eggs that the hen will lay each week? justify your answer. Okay, so we just found the average, right? Which was 5.91, I think, or 5.92. So this is the average number according to our Poisson distribution. Yeah. So this was 5.912. Yeah. Doesn't really matter. 5.9. Okay. So remember that this actually is a distribution that's Poisson. It is discrete, and X stands for the number of eggs. Yeah. So even though 5.9 is the average here, she cannot, or the hen cannot lay 5.9 eggs. So we want to have the most likely number. It can't be 5.9. We know that the Poisson distribution kind of has a maximum here at some point, but of course it's not a continuous one, it's a discrete distribution. That means at some point what we actually have is like a bar graph, and then at some point we have a maximum. Yeah, so if we have this as our values for X, and this is here the probability density function, yeah, that's the probability of each of those happening. And we want to know how many eggs do we have that's actually the maximum, or the most likely. Most likely means highest probability, right? This one here. Now, this of course has to be close to the average number. So we're going to have to check a few. We're going to have to check the probability of laying 5 eggs, the probability of laying 4 eggs, which is a little bit less, and the probability of laying 6 eggs. Because if the average is, for example, here, yeah, if this is 5.9, if this is the average, then we need to check if the one before or after is higher, right? Yeah. Okay. Cool. How do we find these values? Well, we know that X has distribution Poisson with the lambda, that's the value 5.92 that we found before. And now we're looking for something equal with an equal sign. So we're going to go back to the calculator and we're going to go to distribution, which is stats. Oops, sorry, not that one. Menu. The online one on the computer one doesn't work as well as your guys' ones on the that you guys have. So we're going to go to F5 distribution. We're going to find Poisson, which is like F6 and F1. And which one do we take, guys? Remember, if it's equal, it's the one with a P. So make sure you're set under variable, very important. Then X is the value that we want. So let's do 4. And mean is 5.92. That is our parameter. And we're going to just press X. And for 4, we're going to get 0.1374. And then we're going to go back and we're going to just change the number to 5 very quickly. 5 is 0.1627. And we're going to go and check 6 as well. Now you can check more if you want to, but looking at the numbers, I feel pretty comfortable that this shows me which one is the highest. Because here we think that maybe 5 would have been the highest. So we're making sure that before 5 we are lower and after 5 we're also lower. That would show us that that is the most likely one. The Poisson distribution only has one peak. Yeah, so if we know one of them is higher than the one before and after, then that confirms to us that this is the maximum. So writing all of those down and finding the most likely outcome together with a justification. Yeah, so here the numbers here are your justifications. Yeah, we'll give you guys a merit mark, M. There we go. Wonderful. Okay, let's do the next question. Over a period of time, a hen lays 10 eggs. Each egg independently does or does not hatch, with probability 0.65 of hatching. Calculate the probability that 9 or more of the 10 eggs hatch. Okay, so new question, new setup, everything new. So the first thing we need to think about is what is the distribution. So let's call this Y here just to make a change. Y is the number of hatched eggs. So if it's the number of hatched eggs, then we can write down Y has distribution, and now we need to figure it out. So it's giving us a probability, and it's given us independently hatch or does not hatch. I mean, does or does not hatch. There we go. So we have, again, a countable number of eggs. So we are again in the discrete. Yeah, in the discrete distributions. So our options are Poisson and Binomial. To be fair, they've already given you Poisson was the first question. So even if you've got no idea, you can probably guess it's the other one now because they're going to test you on multiple ones. But honestly, go to the distributions and have a look what their parameters are. Yeah. So remember that Binomial, which is the other option here, that's our answer, has two parameters. Yeah. And make sure that that you've got all of the data from the question. If you don't, you probably have the wrong distribution. So we have n and pi. N is the number, a certain number of trials. Well, here we have 10 eggs, so that makes sense. And pi is the probability of success. Success here is hatched. Yeah, we've got the number of hatched eggs. So the probability of success is 0.65. Awesome. Okay, we've got the probability distribution written down. Now we're just going to go and figure out the answer. Here we want the probability that 9 or more hatch. So with other words, the hatched number, y is our hatched number, we want it to be 9 or more. Yeah, so less than or equal to, y is greater or equal to 9. Yeah. Okay, so now we just need to put it in the calculator. But again, what do we have? Remember, an equal sign and a less than and equal to are the only two options. We need to decide. We can't put it in the calculator otherwise, so that doesn't match here. And every time it doesn't match, you guys need to change it around. And how do we do this? Again, we've done a question like this already with opposites. Yeah. So here, this is 9 and 10. This is what we're interested in, 9 and 10. What are the other possibilities? It's 0, 1, 2, all the way till 8. And this is the opposite, of course. They complement each other because one of them is above 9. The other one is everything below. They make up everything together. So we get 1 minus because they are opposites of each other. And we want the probability that y is now less than equal to. And now we check, well, it is allowing 8, everything lower than 8. So this is the number that we need. And the reason why we need that is because this is the number that the calculator wants us to put in, right? So let's chuck that into the calculator. Where's my calculator? There we go. We're going to go back to stats, distribution. We know it's binomial, so it's a 5. And now we have an less than or equal to sign. So we have BCD, the cumulative distribution function. Yeah. And now make sure your variable x is the number that we have less than equal to. So that would be our 8. Our num trials, that's our n. There's 10 eggs, and the probability of success of hatching is 0.65. Cool. Awesome. Let's put that in the calculator. Then we get the probability of greater equal to 9 is 1 minus 0.9140. Which is going to be 0.0860. There we go, which is 4 decimal places. Okay, writing down the probability distribution as well as finding the answer here will give you guys an achieved mark. It's just using the distribution and identifying it. Okay, next part here for B, let's read it. The following figure shows the distribution of the amount of nitrogen fertilizer in tons applied per hectare per year on 332 New Zealand dairy farms. Okay, we can have a look here. Cool. Sorry, it's a little bit of a long question. Move it over. There we go. Using the data in figure 2, suggest a suitable probability distribution. Yeah, we want to suggest one. To model the amount of fertilizer used per hectare per year on New Zealand dairy farms. Assume that the most common amount of nitrate fertilizer applied is 0.16. So the most common is 0.16. State the name and the parameters of your chosen distribution and justify your choice. So the first thing is check which ones you can use. Yeah. Nitrogen fertilizer. Yeah. That is a number that is in tons. So it's measurement. If you have measurement, that is continuous. Yeah. We can have half a ton. We can have that. Before we couldn't have that, like the number of eggs, we can't have half an egg being hatched. Now we can have half a ton. That makes sense. So we know we're continuous. So our options are normal, triangle, uniform, that's it, right? Yeah, just those ones. So we have normal, triangular, and uniform distribution. So which one could it be? Well, if we have normal, what we need is a bell-shaped curve that is symmetric. This does not look symmetric at all, right? Because here we have a tail to the right, it's skewed. So it's not normal, yeah, because it's skewed. Uniform, I guess not, right? We have a peak, and they even tell you that the most common one is this one, leaving us with only the triangular one. And I mean, most of you will probably kind of see triangular kind of seems to be working here. Yeah. So let's write down the distribution here. Let's write down Z is now our random variable that gives us the number of tons. Yeah. And then Z has distribution triangle. And now we have to give the parameters. Remember that is A, B, and C. Yeah, and let me see, I have not added the triangular distribution here, sorry guys. So if we now have a look here, well, we definitely want 0.16, yeah, this is our middle number, yeah, that's our C value. Our least value is 0.1, so that's our A, and our highest value is 0.35. Yeah, this is something that you guys can pick. Now, let's have a look. This is the distribution that we're going to get, kind of like this. Yeah, this is what we have. A is 0.1, B is 0.16. Oh, sorry, B is 0.35, and C is 0.16. It's always in a weird order here, right? Okay, so what else do they want? State the name of the distribution, the parameters, and justify the choice of the distribution. Yeah, so you guys can say that it's continuous. You guys can confirm that this is this has a peak, one peak. Yeah, it has a minimum and a maximum. Yeah, remember normal distribution doesn't have a minimum and maximum. It goes infinite ever so slightly to both sides. And it's not uniform because it has a peak, right? Awesome. So if you pick the correct distribution here, you will get an achieved mark. Yeah, so this part here will be an achieved. Giving a reason for each of the parameters. Yeah, so for example, A is 0.1, which is the minimum value found. Sorry, I can't write. Should probably write it a little bit nicer. Sorry, guys. Yeah, but you guys hear what I say. Yeah, so the minimum value found. B is the maximum value found, 0.35. C is the given as the most common one. Yeah, if you write those things down, you actually get a merit because you're justifying your parameters. And if you want an excellence, you need to get the parameters right. You need to explain the parameters, get the distribution correct, and you have to link it further to the context. Yeah. So by, for example, saying we can see that here is the peak. Yeah, basically it is the same as the merit, just talking about it in terms of the question. Right? Okay. Next question. And here I need to do a little cut, yeah, because I have someone coming over just real quick, and I will see you guys there. Right, next question. So 10 New Zealand dairy farms are chosen at random. Okay, so 10 of them. Use the probability distribution you proposed in part 1 to estimate the probability that more than half of these 10 applied less than 0.16 tons of nitrogen or fertilizer per year. Okay, so what did we have in the previous one? In the previous one, we had a farm is Z, right? Did we call it Z? Yes, Z is triangular. With values, the start was 0. I forgot, 0.1, 0.36, 0.1. B was 0.36 and C was 0.16, I think. Yeah, and 5. Yeah, there we go. Okay, so this was our distribution. And now we're going to use that to calculate what the probability is that more than half of 10 have this. So first of all, we're going to have to calculate how much it would be for one farm. Yeah, because Z here is one farm. And that is the amount of nitrogen fertilizer that one farm has. So one farm's fertilizer. So let's draw it. Yeah, so we have our triangular distribution here. We can just make a start point 0.1, an end point 0.35, and a midpoint somewhere 0.16. It doesn't have to be in the middle or anywhere, or it doesn't have to be to scale. Yeah, so we're just going to draw our triangular distribution here. Okay, and now let's have a look what we're looking for. We want to find out if these farms have less than 1.6. So 1.6 is the part over here, right? And less than is everything to the left. Yeah, remember the continuous distributions, we always calculate an area. So this is the probability that we want to have. Yeah, the probability that Z is less than 0.16. And it doesn't matter if you guys have less than equal to, that's perfectly fine. Yeah, continuous distribution. So how do we do this? We need to find the area. Well, the area here is half times base times height, which is half times. So let's have a look what the base is. Let me just make that a little bit clearer. Half times the base. Well, the base is this part here, right? This is the base. So how do we find that? That is 0.16 minus 0.1, the difference between of them. And now if we wanted to find the height, yeah, the height is this part here of our triangle. So if we want to find that, we need to know what this value here is. Right? This is the height. This is the value that we're looking for. And the height of the values is always given by that formula sheet that you guys have. Now for the top part, yeah, the peak, you guys might remember there's a formula, there's like a little picture in the formula sheet, which says this is 2 divided by B minus A. That's our highest point. So that's what we want. We want the highest point. So the highest point here is 2 divided by 0.35 is B, minus 0.1 is A, and we can put that all together. Let's grab a calculator out real quick and chuck everything in there, because now we have a number and that's the answer, right? So let's go to normal menu, and we're going to go to half times, well, that's 0.06 times, and I mean, remember, you guys can just put this into fractions if you want. So like this, for example, 2 divided by 0.25. You guys can just fill the whole thing in, right? So here we get 0.24. So 0.24 is now the probability that a farm has less than 0.16 nitrogen fertilizer per hectare. So the question is almost done, but lastly, and that's what we marked in yellow, is we want 10 farms. Yeah, so let's go over here for 10 farms. Now, each farm is probably independent of the other, because they probably have their own land, their own places, their own procedures, right? Everything is different. So we can assume that they're independent. Yeah, assume independence. Okay, so what do we want here? We want to have more than 5. Yeah, more than 5 farms. So this would be the probability that x is greater than 5. That's what we want to find. And now here we have independence between each farm. We have a number, 10 farms, yeah, and each of them have a probability of 0.24 of being exactly what we want. Yeah, this is our success. Yeah, 0.24 probability of being less than 0.16. Yeah, this is our part here. Now, this is another distribution. Yeah, if x here is the number of farmers, is it farms? Sorry, the number of farms. Yeah, farms. Then x has a distribution binomial. Because again, we have 10 of them, and we have the probability of success the same as every single one of them, 0.24. So we want to find the probability that x is greater than 5. So we don't do greater than or greater than equal to. We need to have less than or less than equal to. So how do we do that? By doing the opposite. 1 minus. And now we just have to check, well, everything more than 5. So that's 6, 7, 8, 9, 10, and so on. What's the opposite? That is 5 and below. So it's less than equal to, including 5. So now we just need to put that into the calculator. Yeah, so let's do that. We're going to get 5. There we go. And you guys know for now, you go distribution, binomial. We go cumulative distribution, so F2, yeah, B, C, D, because we have the less than equal to sign. Oh, sorry, there we go. And now we have number trials 10, probability of success 0.24, and 5 is the number we're looking for. So we're going to get 1 minus 0.9839. And doing that calculation will give us 0.161. There we go. And I'll kind of move this over so you guys can see. Okay, this is now the probability of having more than 5 farms. So let's have a look. If you guys find the probability of less than 0.16, which is this number here, you guys will get an achieved. And if you guys have this as well as an attempt to calculate the final probability, and I don't really know what they mean with attempt, maybe writing down a distribution but not actually going through with it, or something like maybe something that's wrong, something like 0.24 to the power of 10, which is obviously not correct. Maybe that will count as an attempt. And if you guys get the correct answer here and get to this part, this is an E. Oh, there we go. This is an. All right, welcome to question 3. So let's have a look. Individual cows produce different total amounts of milk over the milking season. For New Zealand dairy cows, suppose the total kilograms of milk per season per cow can be modeled by a normal distribution. Okay, they give you, it's a normal distribution. We have a mean and we have a standard deviation. Very good. So we have x is normal. We have the mean is 4370 and we have the standard deviation is 1350. Perfect. It is known that for the South Island dairy cows, approximately 30% of the cows produce less than 4,290 kilograms of milk per season per cow. Discuss whether the normal distribution model described above appears to be appropriate for the modeling milk production per season per cow for the South Island dairy cows. Okay, so this is the model for the whole of New Zealand, right? And we want to check if that's the same for the South Island. So, well, we have our normal distribution. We have a bell-shaped curve. In the middle, we have the mean, 4370, and we have the standard deviation. Perfect. And now, for the South Island to check is we have 30% of the cows produce less than the number. Okay, so we have a certain number, somewhere less. Yeah, so it's less than the mean. So 4,290. And they say they produce less than that. So that would be this part here. That's our probability. And the question here is this approximately 30%, right? Because then the probability distribution would suit in the South Island as well. So how do we figure this out? Well, what we are looking for is the probability. That's the area under the curve. that x is less than 4,290. And I guess this is already done. This is what all the question needs, because now we can just chuck it into the calculator. So let's go back here all the way to distribution under the stats menu, normal distribution. And again, we have less than or less than equal to, which means we need NCD. Make sure you're under variable. Yeah, and what's the lower value? Well, the lower value is very, very low. So I just do negative numbers and nines, whatever, it doesn't matter. The upper value is 4,290. That's the maximum that we allow. And the standard deviation is 1,350 and 4,370 is the mean. So if we now put that in the calculator, we get a probability of 0.4764. Yeah, so roughly 47.6%. And now if we compare this to what we were given, is that in the South Island, we know that it's approximately 30%. Yeah, so now we need to comment on this and say that 47.6% is much larger than 30%. So what does that mean? The distribution, for the South Island is not appropriate. What I mean here, sorry, that it's not the same, right? Sorry about the bad wording. Yeah, it's not appropriate to use this distribution for the South Island. Awesome. Okay. Milk production data is collected from a herd of 200 dairy cows. Okay, we've got a lot of data there. Okay, we've got the number, the frequency of the cows. Okay, cool. For this herd, 10% of the dairy cows have milk production less than 3,600. Suggest suitable values of the parameters of the normal distribution model that could be used for modeling milk production per season for this particular herd. Okay, so we're told here that this is distribution normal, and they want us to write down the distribution parameters, which would be the mean and the standard deviation. Okay, so let's have a look at what we've got. The mean is quite easy. It should be the middle, right? And it looks like the middle here is about 5,250. So let's use that number there, 5,250 for the middle, for the mean. And now the standard deviation, we need to have a look at how we can calculate this. So we need to actually find the parameter. What we've been given here is part of the distribution. I'm trying to make this a little bit better. Yeah, I'm not very good at drawing these, yeah, but it doesn't really matter for the exam. You guys just draw it. Yeah, so we have 5,250 in the middle, and it's telling us that 10% of the dairy cows have milk production less than 3,600. So 3,600 is somewhere on the left-hand side. Again, it doesn't have to be to scale. It's maybe lower. Yeah, 10% is probably lower. But again, this one is just less than. This is now our area, and it's told that this is 10%, which is 0.1. Right, can you guys see the dot? 0.1. Yeah, is that clear? There we go. So this is all the information that the question is giving us, and we need to use that to find the the standard deviation. Now, every time that they ask you to find the standard deviation for binomial, normal, or Poisson, you guys need to go to the formula sheet, and you guys need to have a look at the formula, and it tells you in the formula sheet that z is equal to x minus the mean divided by the standard deviation. So this is now our formula that we have to use to find the standard deviation. So how are we going to do that? Well, if you guys remember, if you guys did this last year in probability, you have to draw a second graph, basically the same, but with different parameters. Yeah, this is the standard normal distribution, and I am absolutely terrible at drawing these right now. There we go, something like this. Yeah. So the standard normal distribution has always got the mean 0 and the standard deviation 1. So we need to transform our graph to suit these values. Yeah, so we have 0 in the middle. And now the only thing that doesn't change is the probability. Yeah, so it's still on this side and it's still 0.1. That's still the probability. But now what we can find is this z value. Yeah, this is the standard normal distribution, which has a z instead of an x. Well, if we now go and follow through, we can go to our calculator and actually ask them to find this for us. So if we're going to go to distribution, normal, and now we're trying to find, let me do this so we have more space. We're trying to find a value, not a probability. And anytime you're trying to find a value instead of a probability, you need to use the inverse instead. So if we go to inverse now, make sure you're under variable. Now it's asking where the tail is. Well, the tail, it always requires you to be at the very end here. Yeah, you can switch this to the middle if you have something like this. Yeah, in where the area is in the middle. So, sorry, the center would be, of course, symmetrical in the middle. Yeah, otherwise you need to put it into different parts. Okay, the tail here is to the left, and the area here is the probability. What is it doing? Send feedback, no? Ah, there we go. Okay, so the area is 0.1. Standard deviation is 1 and the mean is 0. Yeah, that's the standard normal distribution. Yeah, and we're going to get, and it says x inverse. Yeah, so that's the z value. Yeah, so the z value here is minus 1.28, and be very, very careful. I have had many of my students simply forget the negative. Yeah, it's very hard to see the little negative that's over here. Yeah. By the way, you guys can tell if it's going to be negative or positive because in the standard normal distribution, everything on the left-hand side is negative and everything on the right-hand side is going to be positive. Okay, so now we have our formula. Z is equal to x minus the mean divided by the standard deviation. And now we just substitute in our values and we find the standard deviation. Well, the z value we just found is minus 1.28155 is equal to, and now the x value, yeah? So what I want you to remember is the z value is the number that we're interested in for the standard normal graph, and the x value is the same number but for the original graph, yeah? So in this case, this is the 3,600. And the mean is given to us. Well, the mean and the standard deviation is, of course, everything goes back to our original. Otherwise, it would all be always 0 and 1. Yeah. So the mean was given as, well, that's what we chose, 5,250. And the standard deviation is what we don't know. And now you guys can happily multiply both sides by the standard deviation and find out what the numbers are. Yeah. But if you guys don't feel comfortable doing algebra, yeah, then you can do the same again as what we did in the other past paper, or was it in this one? I think the other one, where you go into the solver. So we're going to go to menu and we're going to go to equation at the bottom, and it's F3, the solver. And now we're going to, I always like delete and then delete all. I like to have it completely cleared. Yeah, and now we're going to enter this. So it's going to be minus 1.28155, and then the equal sign is at the bottom of the calculator here, at least for me. And then there's a fraction. Yeah, you guys can type it in exactly how you guys normally have it. 3,600 minus 5250 divided by, and now you can't put the standard deviation because the solver always uses x, and that's this button here with an x. And now remember, you guys have to just press execute a few times, yeah, just to make sure it doesn't change anymore. I think it's always at least twice. And now you can read what x is. So x is our standard deviation here. So that is 1,287. I guess 0.5. We can do 1 decimal. Yeah, that's perfectly fine. Awesome. Okay, so now we have found our standard deviation and our mean. And we have answered the question, therefore, fully. Yeah, so it's a little bit small there, the question. There's so much writing in these. Okay, so finding the standard deviation or anything close to that. Yeah, now we'll give you guys a mark. Okay. Now let's have a look. What else do we have here? That sounds good. Okay, cool. Perfect. Oh, I didn't tell you what you guys get. You guys need to find the mean or the standard deviation. So I guess if you guys have 5,250 here, that will be your achieved mark. And if you find both of them, then that will be your merit mark. But I mean, if you find both of them, you have to find the mean automatically to find the standard deviation. So okay, next question. Compare the normal distribution models for the total kilograms of milk per season per cow produced by the 200 cows in part 2 and the total kilograms of milk per season per cow produced by all of New Zealand cows. Make at least 2 comments and support your discussion with conclusions and sketches where appropriate. Okay, so let's talk about the parameters first. Yeah, we're going to have 2. One of them is, I'm going to call this the 200 one, and the New Zealand distribution. Let's make this a little bit smaller. There you go, so it's not so thick. Yeah, okay. So these are the 2 parts, and we're going to compare them. So let's make it a little bit more space. There we go. Cool. Okay, for the distribution, we just need to have a look at the numbers. So in part 2, that was this one here. We had 5250 and 1288. Let's round it up. So that's the one that we had before. We had the mean is 5250 and the standard deviation was 1287.5. So let's make it 1288. For New Zealand, let's go back to the question. The numbers were 4,370 and 1,350. Okay, so let's write that down as well. The mean was 4,370 and the standard deviation is 1350. Okay, wonderful. So this is kind of the part where we have all the information. Yeah, so make at least 2 comments and support your discussion with calculation and sketches. Okay, so first of all, the first thing that I would say, yeah, to compare them, is that the New Zealand one has a lower mean. Right, the New Zealand one has a lower mean, we can see that, but it has a higher standard deviation. Yeah, so what does that mean? That means if we look at the 2 graphs, for example, one of them is going to be here. I should make it much smaller. There we go. And not in 0. Go. One of them is here. Yeah, this is the 4,370. And the other one is maybe a little bit higher. So maybe around here at 5,250. Yeah, this is maybe not accurate. Yeah, but we have a shift here. So the next part that we have is we can talk about the spread. So let's make some calculations for the spread. And remember that for the normal distribution, what we are interested in is the range, yeah, and maybe the 95% quartile. Yeah, the 95% quartile is if we are 2 standard deviations away from the mean. So this is the 95th percentile of the data in the normal distribution, which is the mean minus 2 standard deviations and the mean plus 2 standard deviations. And we're 2 standard deviations away from the middle. So let's do the 95% range of values for both. Well, the mean, let's go to calculator. Can I please use it? Yep, there we go. Let's go back to our original calculator. For the 200 group, we have 5,250. And we're going to add 2 times 1,288, which was our standard deviation. Yeah, so if we're adding it, that's our maximum. So that's 7826. And then we're going to go back and do the same calculation, but we're going to subtract it. And that is 2,674. So this is the values that 95% go between for our cows, for the 200 cow example. And now for the other one, we have 4,370 minus 2 times 1,350, which will give us 1,670 all the way till, and let's go back real quick and make it a quick plus, which is 7070. Yeah, so what we can see here is the range here is different than here. Yeah. Okay, we start much lower over here. Yeah, for the New Zealand one, we start much lower, but we almost get to the same maximum, very close, right? Maybe 800 off. And that's because obviously the standard deviation, yeah, is higher. And that makes sense because our range is also higher. Yeah, different spread for our normal distributions. Okay, so we've compared the center, we've compared the spread. The shape is obviously the same because they both are normal distributions. Is there anything else that we could maybe talk about? I guess anything that we've now talked about in context, talking about it a little bit, you guys can write your text at the bottom. Yeah, you can write your answers. Yeah. You guys have a lot of time to answer these questions here in the actual exam. So talk about it exactly like we did, comparing the numbers, which one is higher, which one is lower, make some calculations. Now, if you have one valid comparison, then you get an achieved. If you have two valid comparisons, that is a merit. And if you have two valid comparisons, but you talk about it and explain them in context and relate them back to the numbers and calculations that you've done, then you get an excellence for this question. Yeah, so 1 for A, 2 for merit, and then 2 plus explain, yeah, for your E. Okay, yes, we always have one of those questions in the exam where they give you a certain table, yeah. This is the distribution. So the table below shows the probability distribution of a random variable n, the number of goat kids, baby goats, born per pregnancy for this type of dairy goat. So here, what can we see? We can see that n takes values, yeah, n takes values 0, 1, 2, 3, or 4. This is the only values that n can possibly take, yeah, and this is a kind of made up one, yeah. So I usually like to have these in a probability function, yeah. So something like the probability that n is equal to n, and then we have a function which gives us, similar to the triangular one, and then the numbers 0.1, 0.12, 0.75, 0.02, and 0.01. And that is for 0, 1, 2, 3, and 4. Yeah, but it doesn't really matter if they give it to you, if they give it to you in a table or if they give it to you as a function. Yeah, this is similar like the triangular one. Yeah, where there's different categories and you check where you are and that tells you then the probability. So calculate the mean and the standard deviation of the number of goats. I mean, this is a very easy question. This is 3 marks every single time you guys get this question. All you got to do is know how to put it in the calculator. So let's grab the calculator. We're going to go and put the data exactly in the table, just like we have in the question. We're going to go to stats or table stats, right? Yeah, stats. Yep. And we're going to delete everything that we have here. And on the list one, on the first one, we put all the values that are possible. So 0, 1, 2, 3, 4, and it doesn't even matter which order. And now in the second list, we're going to put the matching ones. Now make sure that these match if you change the order. Yeah, 0.75, 0.02, and 0.01. And now what we're going to press is we're going to go to calculate, but we want to press variable 1. Yeah, we want to calculate for variable 1. However, we first need to make sure that things are set up correctly. Yeah, so always make sure that the first part, one variable, is list 1. That's our first one. And then for the second one, for the frequency, yeah, that is set to list 2. Sometimes if you reset the calculator when you do your exam, you need to change this from 1 to list and then select the second list. Otherwise, it will not work. So now we can press variable 1 and we get all of our values for free. So the mean is given to us as 1.72. And if you really want to say, you can just say, I used the calculator. Yeah, and they don't really care. Yeah, they just mark you as you've got this and done. And standard deviation is also there. That's the standard deviation here with the x in the end. So it's 0.7. Yeah, 0.708. 3 decimal places here should be okay. Yeah. So this is a free question. It's a free achieved mark. Just to put them in the calculator, knowing how to do it, it already gives you an achieved mark that is easy as. Yeah. Okay. Next question. Dairy goat farmers prefer types of dairy goat that produce an average of 2 goat kids per pregnancy. Comment on whether or not this data suggests that this type of dairy goat will be a good choice for a dairy goat farmer. Okay. So now everything that we've had before, we just need to kind of check, does that make sense? So here we have an average of 2 goats. So we have 2 newborns. Yeah. So that's kind of this number here. And oops, sorry about that. We also have 75% here, which is the highest, right? So this is very common. Okay. Comment on whether or not this data suggests that this type of dairy goat will be a good choice for the farmers. So we can comment on it using the information that we've got before, right? If the mean is 1.72, yeah, then the average number that they have is 2, which is larger, right? So here the average is 2. Yeah, so the average is larger. Yeah. So what does that mean? That means they have more goats, right? They have on average more. And that kind of depends what they want, right? Do they want this kind of goat? Do they want to have more? Do they want to have more kids, more goat kids? Yeah, if they do, yeah, if they want as many as possible, then this would be really good for them. And also we can compare the standard deviation. Yeah. I mean, here we have 0.71. Yeah. So what does that mean? That means we are about 0.7 away on average from the mean for both sides. Now this is less than 1. So that means that we are not really skipping too much, right? Whatever the maximum number is, it's either 1 less or 1 more. Yeah. Okay. Let's have a look what we need to talk about here. We need to talk about both the mean and the standard deviation here. Okay. I mean, I guess they make you find it in the question before, and then you have to talk about it, which makes sense. Okay. Cool. So these goats here, what's our final answer? Let's write our final answer here. So the goat that we have here may not be suitable. So not suitable. Yeah. Because the mean is larger. Yeah. And what else do we want to talk about? We want to talk about the standard deviation, which means that these are less than 1. So standard deviation is less than 1. That's what I would say, which means there's not much change. Yeah. Awesome. Okay. For these goats, what does that mean? We would have about 2 is our average, and the standard deviation is less than 1 less. So we have between 1 and 3, but kind of in between, right? So in between here. Yeah. So, oh, sorry, I can move that up. Okay. Talking about both and comparing it with anything suitable, like literally anything you guys have to say to compare the mean and the standard deviation here will give you guys a merit mark. There's no achieved mark for this question. Okay, next question. Suppose that with improved nutrition of goats throughout the year, the proportion of pregnancies that result in 2 or more goat kids changes. Okay. The table below shows the probability distribution of a random variable n, the number of goat kids born per pregnancy for this type of dairy goat with improved nutrition for goats throughout the year. Okay, cool. We've got different probabilities now. Same thing. Without further calculations. Okay, so we're not allowed to do anything. Use statistical reasoning to explain what effect this change in probabilities would have on the expected value and standard deviation of the number of goat kids per pregnancy. Okay. So we're not actually supposed to put it in a calculator. You can, right? You can to give yourself an idea, just don't write it down, right? And you will see a couple of changes, right? And the one thing that we see here, if we look at it, is that 2 has now got a lower number, yeah? So that the mean will probably be a little bit different here, yeah? And how will it change? Well, it looks like the numbers next to it, a quarter and 10% roughly, or 7% is still somewhat big. So let's have a look at the previous one. So here we had basically one number in the middle, right? And then nothing on the top, yeah? That means that the mean will be somewhere between those two numbers. Yeah, there's basically nothing here. And let's have a look what happens. Also we have large numbers below, but very low numbers above. So here we are currently at 2, which is 53%. And then above that, we still have quite a bit, right? Here we have about 37% altogether. Yeah. And at the bottom here, we have only 10%, which is less. Yeah. So what would that make as a change? Yeah. So first of all, on the expected value, remember that's the mean. Yeah. And I'll just explain it to you and make some notes. Yeah. It would increase. So, and what I would write is exactly what we talked about, that there's only 50% of the, or 53% of the probability on 2, and together with the 0.1, 0.03 and 0.04, 7, sorry. There's not too much change going towards to the left. Yeah, so we're increasing it here because 3 has a high probability with 0.25. And yeah, there's not really too much more I would say here. We still have the same range from 0 to 4. Yeah, so that doesn't change, but 4 is much more likely, right? So it's going to pull up that mean, and it's actually going to be above 2. Yeah, so the mean is greater than 2. Now for the standard deviation, well, the standard deviation is how far the data is apart. So let's have a look again at the other one. And this is again what we will talk about. Yeah, majority of the probability here is at 2. And there's not much above. And there's only a little bit as well on the left-hand side going towards 0 and 1. Yeah, so that's these values and these values. So the extreme values 4 and 0 are, have very low probability. So they're very much compacted together where the 2 is. Yeah, so that's what I would say. And then I would compare to this one, say this is not the case here because we have 50% only, or 53%, and the remaining of it is distributed to the other parts. Yeah, I would also say that 4 is now much higher. Yeah, so that means 4 is going to move our distribution further up, increase the range. Yeah, so the effect on the standard deviation here would be that the standard deviation is increasing as well. Yeah, and again, I would comment on how far away we are. Yeah, and what the numbers are. I think you would actually be able to do, because you're not allowed to make any calculations, you're allowed to say majority of it as long as it kind of makes sense statistically. Potentially you could say, yeah, but maybe the standard deviation could maybe be similar, because here at the top, I mean, we have quite a bit here, yeah, 0.22, and then nothing on the top, and then on the other side here, yeah, I mean, we have a little bit more. Yeah, it's probably going to increase, but I'm just wondering if you would be able to get a mark for saying it's roughly the same, or maybe a little bit increased. Let's have a look at what the marking schedule wants, right? Let's have a look. So, change in mean. There's a higher concentration of proportions for 2 or more. Yeah, absolutely. So the expected value will increase. Perfect. We need to talk about that. We need to explain it. And that will give us 1 mark. That will give us an achieved. And talking about the other one and explaining it will give us a merit. And if we do both of them, then we get a E. Okay. So, no credit awarded for calculations. We know that. Explanation must come from the description. We know that as well. That's actually very funny because I wish I could blend this and maybe I'll put it in the editing part, but the marking schedule actually tells us the probability of most common numbers of goat kids is now reduced to 0.53 from 0.75, which is exactly what we said. The proportions of the number of kids being born used to be mostly concentrated around 2, but now they are more evenly spread across 1 to 4, meaning the standard deviation will increase. Okay, yeah, so exactly the same as what we've got. Talking about one of them will give you an achieved. Maybe I'll write it a little bit different here. So if we talk about 1, that's an achieved. About the no, we need to, yeah, sorry about guys, we need to actually talk about the standard deviation to get a merit, and the achieved is the expected value, and the E is for both. Wonderful, perfect. That looks good. That was a nice paper. Yeah, I like this one. Okay, I've got all of the other years available as well. So make sure that you guys take a break, go back to the questions that you guys struggled with, take some notes, take a break, and then come back to another example, hopefully a day or 2 apart, so you guys can remember some of these parts. And make sure you join the Discord if you guys want to ask specific questions. Yeah, as I've said in the introduction here. Yeah, if you made it so far, please put something nice in the comments and let me know that you've made it all the way through this long video. I really appreciate it. And like the comment, I'll see you in the next one.